Hi, thanks to the conference organizers for inviting me. My name is Jake Vanderplas. I'm an astronomer at the University of Washington, and I'm going to talk about a telescope project that my group at UW is working on called LSST, and how we're using Python with LSST to explore the universe. So it might be a little bit different than the other talks that you see here this weekend. But so just to set the context, in astronomy we have this long history of people looking up at the sky through telescopes going all the way back to Galileo. And I like to think of the classic astronomer as sort of typified by Edwin Hubble. You know, he was this guy in the early 20th century who used large telescopes to look up at the sky and learn some really interesting things about what was going on outside our galaxy. And when I talk to most people, this is what they think of an astronomer. You know, someone who has this nice big telescope on the top of some mountain and goes up there and looks through the eyepiece and learns about the universe. Of course, as you know, we've come a long way from there. And today we have instruments like the Hubble Space Telescope, named after Edwin Hubble, that's up there. It has a digital CCD that allows us to take very, very detailed images of very distant galaxies and objects. And so we've learned a lot from Hubble, but moving on from there, we've done some other things as well. And recently, astronomy has moved towards what we call survey astronomy, or survey science. And this is probably best typified by a project called the Sloan Digital Sky Survey. And the Sloan Digital Sky Survey was this telescope right here. It's situated on the top of a mountain about 3,000 meters on Apache Point in New Mexico. And what the Sloan Digital Sky Survey did is it was an automated survey that ran for, well, the main survey was about 6 to 8 years, and it's actually still going now. There's more iterations of it. And the initial goal of the Sloan Digital Sky Survey was to map in great detail the locations and distances to distant galaxies. And I apologize for the projection here, but if you look closely, you can see this. This is the three-dimensional map that was created by the Sloan Digital Sky Survey. At the very center of that is our location in the universe, and each of those dots going outwards is a galaxy that's up to redshift 0.14, which is hundreds. How far would that be? Dozens of, no, I always have to convert this. It's hundreds of megaparsecs away, which is something like 300 million light years out to the edge of that. So this is the kind of stuff that we're doing now. And moving forward with survey science, with survey astronomy, we're looking towards the future, and basically the data volumes are going to grow. And the project that my group at UW is working on is this so-called Large Synoptic Survey Telescope. And I'm going to refer to this as LSST throughout the talk. And just for reference here, here's a typical person. I don't know, 6 feet tall, or however tall a typical person is. And so you can see this is an extremely large telescope. Well, we'll get into the size of it in a second, but the key part of this is that the LSST is going to scan the entire night sky in an automated fashion and produce an incredible amount of data. So the short blurb that I like to give is LSST it's an optical to near-infrared survey, so the kind of light that we can see and then just a little bit more to the red. And it will do a survey of the entire southern sky that will end up being basically a digital movie. It'll take pictures one after another, and we'll have a 10-year-long movie of the southern sky. And so the LSST telescope is going to sit in one of the driest places in the world, the Atacama Desert up in Chile, up in the mountains. You can see there are already some telescopes that are up there, the Gemini Observatory, the SOAR Observatory, and LSST will be built on a nearby mountaintop. The the site work has already been started here. So there's a nice cleared out site on the top of the mountain. A big part of this telescope was actually building the road up to the top of the mountain. It's a huge cost in creating it. And you can see the location down there in Chile. And the important piece of this is that it's extremely dry, so that I think the rainfall is only a few millimeters a year or something like that. So it means that we can have almost continual observing time as the year goes by. So pieces of the LSST have been formed already. On the left up here, you see the primary mirror of the LSST. And this is the primary mirror blank down in being built in Arizona right now with a lot of the LSST team. And it's 8.4 meters in diameter, so it will be able to gather an incredible amount of light. And on the right here, we see a mock-up of the CCD for LSST in real size. That's Suzanne Jacoby right there. She's the outreach coordinator for LSST. So essentially, in your cell phone, you have a CCD that's about that big. Imagine expanding that up to about a meter in diameter. This is the CCD that will gather the light, and it means that LSST has an incredibly large field of view. This is about the size of the projection of the full moon onto the CCD. So you can imagine the size of that on the sky. Because of that large field of view, LSST will be able to survey the entire sky incredibly quickly. So just quick stats on it. It's basically going to do the full southern sky every 3 to 4 nights. So basically scanning the sky, after 3 nights, it will have scanned the entire sky. And that data rate is going to be about 30,000 gigabytes per night that we're going to be processing in real time. An important component of that 30,000 gigabytes a night is that we want to do real-time processing. Because we're looking for changes in the universe, things that are changing night to night, we want to be able to process those images within about 60 seconds so that we can send out alerts to the astronomy community so that they can use their other telescopes to follow up and learn about things. And the final catalog at the end of 10 years is going to be on the order of hundreds of petabytes. So it's an extremely large project, and because it's so large, we have a lot of people working on it. These are all the partner institutions. A number of astronomers and researchers at each of those. I want to highlight just a couple. University of Washington, that's where I'm from. UW is home to the image simulation team, which I'll talk about in a second. The way that I got involved is I did my PhD at University of Washington under Andy Connolly, and he's one of the lead scientists for the project. So I got involved as a grad student, and now as a postdoc, I'm continuing my involvement in the project. And I should also point out, too, because a couple of people have asked me already, Google has signed on and is being contracted to handle the database side of things. So we're going to have a database down in Chile itself, and then also some mirror sites on the U.S. mainland. So some of those details are being handled by people who are good at big data. So a big question with this is this sort of data stream is completely unprecedented. I told you about the Sloan Digital Sky Survey. That's kind of the flagship data set that we have in astronomy right now. LSST is going to produce a Sloan Digital Sky Survey every night for 10 years. And when SDSS ramped up, it got its first data. It took a while for astronomers to know how to use it. We had to figure out the format of the data, what sort of characteristics there were, how to clean it, how to learn the things we want to do. So it took about a year for papers from SDSS to start coming out. And you can imagine that might be a problem with LSST. We have this continuous Sloan Digital Sky Survey every night coming in. If we don't get on it right from the beginning and learn how to work with the data, we're gonna fall behind and just be overwhelmed by the data rate. So in order to address that, we've undertaken a huge image simulation program. And here's an animation of what's going on. Essentially what we're doing is we are simulating down to the level of the individual photon, every single aspect of the survey as far as we can understand it. We start by creating a virtual universe based on our understanding of everything that's out there. And these virtual galaxies and virtual stars all create photons. And the photons come down through those first few lines. Those are atmospheric models that model how the photons deflect as they go through the air in the atmosphere. Then we come down, and at the bottom we see the primary mirror right here. So the photons hit the primary mirror, and then bounce up to the secondary mirror, down to the tertiary mirror. We have a zoom in of the tertiary mirror and camera setup right in here. And you can see that some photons scatter outside the camera. They don't land on the CCD. And then this right here is an image of the CCD, the place where the photons finally land. And then beyond that, once we hit the CCD, we're simulating the physics of the CCD itself. So each of those photons land on the substrate and knock out an electron, and the electrons up there cross the voltage, the boundary, and are detected. And from that, we're able to build up, from our best understanding, very realistic images of what the LSST is going to produce once it finally gets started. So just to show you a little bit what goes on in this simulation, if you start with a point source, basically a star that's a perfect point in space, we go from the upper left across and down, and this is how the various components of the simulation end up constructing an image. So we have the optical model of the telescope, we have tracking, so basically as the Earth is moving, the telescope needs to move to follow the sky, otherwise we lose precision. So there are tracking errors, there's diffraction in the atmosphere, there's diffraction within the telescope, there are perturbations on the lens, little micron-sized perturbations or less than that in the actual material of the lens. Then we have our detector, our dome seeing, that's basically what's going on, air currents around the telescope dome that protect the optics, and then atmosphere, high altitude atmosphere, and finally pixelization. So a point of light out in space turns into a pixelization that looks like this. And by modeling all that, we can produce very, very realistic images of what the sky would look like. You show this to an astronomer and ask them whether it's real or fake, and we're to the point now where a trained astronomer wouldn't be able to recognize whether that's a fake image. And this is actually a simulated image from the LSST pipeline. So the hope is that by getting this spun up and by getting people kind of trained on fake data, that when first light happens in 2019 or so, when the first science data comes down, the community will be ready on day one, and it'd be great if we had people writing papers by the end of that first week, and I think it could happen. So this is just a quick diagram of what's going on in these simulations. That big orange thing up there is the piece that a lot of my colleagues work on, and this is a model of the observable universe, and it's really, really fun because we have to take basically a synthesis of everything we know in the history of astronomy and use that to create a generative model of what's up there in space. Everything from the nearby universe, asteroids that are near the Earth's orbit, all the way to other stars in our galaxy, and even to other galaxies way out towards the edge of the universe, quasars and things like that. And I'm not going to go through all these pieces, but just to show you, we're thinking about all these different things. And another aspect of this is we can use this to test the cadence of the LSST. We can use it to figure out how we should design the survey to observe the sky in order to learn the most about our science goals. So it's a pretty interesting program. Now, because the LSST is a time domain survey, we're looking at looking for the way things change from night to night. So a key component is this what we call difference imaging. So you take an exposure from one night, an exposure from the next night. And does anybody see the difference between those? Yeah, when you compare these and subtract them, you find that the difference is this dot in the middle. And this is an observation of a supernova. This is an exploding star inside our galaxy. And from one image to another, it became very, very bright. And what's going to be interesting with LSST is there are going to be about 2 million of these events, 2 million significant differences per night. And of those, about 500,000 are random fluctuations. If you just do the Poisson statistics on the error in each pixel, we'll have about 500,000 random. And a vast majority of those are just going to be things like asteroids moving around and stochastic variability in stars and things like that. But with about several thousand or so are quote-unquote interesting sources of variability. And these are things like supernova, like planets crossing in front of their stars, like all sorts of things that people are interested in. So in order to alert people of what's going on in the universe, we're going to have this real-time alert stream that will basically, within 60 seconds of taking an exposure, will categorize each of these events. And you can think of it as like a Twitter stream where there's a hashtag label on, if you're interested in supernova, you follow the LSST stream and look for certain types of supernova. And then the idea would be that if you're an astronomer who has access to another telescope and you're interested in these objects, you can go back and follow up. And that same night that they're happening, you can get more observations and learn about what's going on. So this is just an example of a supernova in 2011 that was discovered. So you guys might have heard of dark energy. This is that concept that came out about 15 years ago. Astronomers discovered that the universe is expanding. The rate of expansion of the universe is actually accelerating, which was completely unexpected for a lot of reasons. And that dark energy was discovered based on observations of about 100 supernovae by these teams in the late 90s. By contrast, LSST is going to find millions of these supernovae, so it'll give us a much better tracer of things like the expansion of the universe. So my area of study was cosmology, the study of the universe as a whole, looking at the expansion rate of the universe, how much matter there is, how much dark matter there is, to what extent dark energy drives the expansion. And these are just some of the areas that LSST will give us some insight into these cosmology things. It's going to find so-called baryon oscillations. This is basically in the early plasma in the universe, there were sound waves, and those sound waves got frozen out when the subatomic particles recombined. And the cool thing is those sound waves are now imprinted on the distribution of galaxies. So by looking at the detailed location of galaxies in 3 dimensions, you can learn about the fundamental thermodynamics at the beginning of the universe, which just blows my mind. I think it's so cool. LSST will tell us about that. We'll learn about, through gravitational lensing, we'll learn a measure of the geometry of the universe. Gravitational lensing is where light is basically bent by strong gravitational fields. And I get excited about this because this was the area of my PhD thesis. I already mentioned supernovae. We'll find a lot of those. And then we'll also be able to learn about clustering, measuring the growth of the large-scale structure in the universe. In the transient universe, transients are things that change from night to night. The LSST is going to give us an insight into a lot of different things. We have transiting planets, so planets around other stars that might pass in front of those stars occasionally. And as they pass in front, it makes it just slightly less bright. So by monitoring all these stars with LSST, we might be able to discover these extrasolar planets, similar to the Kepler mission that's happening, or that just finished up. We'll find these supernovae. We'll find gamma ray bursts. These are really, really energetic events linked to black holes and neutron stars. We'll find quasars. Quasars are they're the radiation caused by supermassive black holes at the center of distant galaxies. There's some of these black holes out there that are 10 to 100 million times the mass of our sun. just gigantic things. And their gravity is pulling in dust and gas, and as that dust and gas collides with the other dust and gas, it heats up and creates X-rays, and those X-rays, due to the physics going on, and can be kind of funneled out, and quasars are very cool. We'll learn about those. We'll learn about stellar flares, variability, and one of the important things is asteroids and comets. LSST will help us track some of the near-Earth asteroids and potentially find ones that might in the future be dangerous to Earth and us as humans. So that's a big component of it. And just to show you one cool result that can come from difference imaging, this is from the CTIO survey, and this is a picture of the Large Magellanic Cloud, which is a small galaxy that orbits the Milky Way. And through difference imaging, you find something really interesting. If you take this image and subtract it from one that was taken just a few months later, you get something that looks like that. And a year later, the difference looks like this. And as you continue, this difference gets bigger and bigger. And you see these concentric circles here. And this is kind of a strange thing. You know, why would you see concentric circles that are growing in the difference from one image to the next? And what's going on here, this is well known that this was what we call a light echo from this famous supernova called 1987A. And the way to think about it is this star blew up and shined and started sending out radiation, really, really bright radiation. And as that radiation traveled out, it hit dust and scattered off the dust and bounced toward us. So as time goes on, if I flip through this, you can see that year to year, these rings are growing. And the reason they're growing is because that light is spreading out and bouncing towards us. So by using the triangulation, we can basically compute a very, very accurate distance to this supernova. And we can also learn other things about it. And so the thing we can imagine here is it gives us kind of a window into supernovae that happened a long time ago in the past. So people have, based on these sorts of principles, people have gone out and tried to look for things like the remnants of the supernova observed by Kepler and other famous historical supernovae that have been recorded by humanity. So there's some really cool stuff you can do with all that. Difference imaging, though, is kind of difficult. It's not as easy as just taking one array and subtracting another. And the reason is because we have the science image that's basically the image built up over the years leading up to that time. And that has very different noise characteristics, very different point spread function than the nightly images. So we have to rotate and align them. We have to detect sources on them. We have to use those point sources to model the point spread function. When I say point spread function, I'm referring to what we saw in that simulation earlier, where a point in space turns out to be kind of smeared out on the detector. The degree of that smearing changes from night to night and from hour to hour. So we have to model that very carefully to do these difference imaging. And when we deconvolve it and subtract, and we end up with finding these little differences. So it's a really interesting problem. And again, I have a big diagram of the framework that's going on underneath to make this happen. Essentially, the gist of this is that we have the data coming in the yellow over there, the data acquisition. It goes into a database where we kind of update a model of what the sky looks like. And then for each of those new images, we compare it to the model, and we can use that to find what's going on, what's changing night to night. So it's a big pipeline with lots and lots of very intensive computation. And we want to do this in real time. And to do it in real time, it's going to take about 10,000 CPUs running our pipeline software down there, right near the telescope in Chile. So where does Python come into all this? I told you that I'm going to tell you about how how we use Python to explore the universe. Essentially, what we've done is the core of the software is a C++ object model. So this has been written over the last 10 years or so. And because we want astronomers to be able to use this, we want this pipeline to be useful for many surveys in the future. We've put together a SWIG binding layer that basically mirrors the object model in Python. And this has been challenging for a few reasons, but it's working out pretty well. And the reason we're doing this is because astronomers don't write C++ code. Astronomers like to work with their dynamic, interpreted, interactive languages. And so for that reason, we're using Python as the binding layer. And the idea would be that people could go in and use this software, kind of use it as a standard library for doing these astronomical calculations in the future. So you might ask, why Python? The answer to that is pretty complicated, but a few of the reasons that we've chosen it is because it is dynamic, interactive, and easy to learn. It's been really well used in astronomy. It's been adopted pretty heavily over the last 10 years especially. We like the fact that it's open source and cross-platform. Another framework that's been used pretty heavily in astronomy is IDL, the Interactive Data Language. And one issue with that is that it's a proprietary system. So it means that if you want to run 100 cores of IDL, you have to have 100 site licenses. And occasionally this comes up because, at UW, I think we have 100 or 200 site licenses for IDL. So if someone spins up a parallel job with IDL, they use all the site licenses, and then no one else in the department can do their research. So proprietary things are difficult for a number of reasons. But Python's open, and we like that. And also, Python provides this really nice interface to compiled languages like C, C++, Fortran. Those tools are very well developed, and we can use our code that's been developed over the course of years in astronomy. There's also an excellent core of scientific packages in Python. I'm not sure how familiar this crowd is with these, but NumPy and SciPy, Matplotlib, and Ipython basically provide a framework for very efficient data-intensive computing, interactive data-intensive computing. And around these, we'll hear about Ipython a little later. Min Regan-Kelly is here and is going to talk about that on Sunday. Around these kind of core packages, we have all sorts of third-party packages that have been developed to do various things, like machine learning, astronomy-specific things, loading different data types, doing network analysis, and things like this. So the Python scientific ecosystem is really, really strong, and we can do a lot of interesting things with it. Another piece that just in the last year has become very important in Python is this Ipython Notebook. It's a way of sharing code, sharing data, sharing graphics and analysis all in one package where it can be basically executed and reproduced very easily. And hopefully Min will talk about that a little bit more in his talk Sunday. And this comes to, I'm going to indulge and go into my own little soapbox really quickly. My soapbox is about reproducibility. The Ipython Notebook really allows us to step into reproducible science. And this is becoming more and more important as things are more and more data-driven. So one infamous example is this Reinhard Rogoff paper from economics that you might have read about. Basically, these are two Harvard economists who published a paper doing some analysis and they made the claim that if you have a certain debt to GDP ratio, then after that your economy is just going to stop growing. And this was picked up by one of the parties in American politics and kind of used as a core principle of their economic plan. Now, there was a UMass Amherst grad student named Thomas Hendren who went out and wanted to, since this was such an important result, he wanted to replicate it. So he went and tried to replicate it, and he wasn't able to. Based on existing data, he wasn't able to do it. So he went and he asked Reinhard Rogoff for their spreadsheet. They were doing their analysis in Excel. And he looked at the spreadsheet and found that they had basically made an error. They forgot to include some columns in their average, and that changed the result. And so from there, he and his advisors published a paper that was basically talking about how this really important paper published by Harvard economists was wrong. And it caused this whole flurry of debate. And regardless of what side of the politics you're on, I think we can all agree that it would be better if that information and that data wasn't hidden in an Excel spreadsheet that you have to email the authors for. And just as an example of what you might do with the Ipython Notebook, there's this website here. I have the website right there. As someone who has reproduced this whole thing in an Ipython notebook. And with this, you can take that notebook and you can rerun all the code cell by cell and understand what's going on and see where the numbers are coming from. So my claim is that if people adopted the Ipython notebook or a similar platform and published the results in a way where the reader could rerun code and reproduce what's going on, that we would be in a much better place in many, many scientific fields. So this is my claim that I like to make. If it's not reproducible, it's not science. So you got to be doing your stuff reproducible. Our efforts in this area, real briefly, we've put together a Python project called Astro Ml. It's machine learning for astronomy and astrophysics. And essentially, this website right here has hundreds and hundreds of examples of using real astronomical data, doing machine learning tasks on those. It's astroml.org. You can read about it if you want to. This has been my big push over the last year and a half. So just to show you there, we have examples of different analyses with the code that loads the data and does the analysis, and then we have plots. And I'll just spin through it because I'm out of time. But essentially, we have 200 plus examples of real analysis on real data. And the thing I'm excited about is we already have several papers that have been published where the plots and the analysis and the data from the paper are on Astro Ml. So this is something we're pushing for and hoping that it'll change astronomy for the better. So just real quick, in summary, I told you about LSST. This is this decade-long survey that'll create a movie of the entire southern sky. It's really going to change the way astronomy is done, and I'm not just saying that because I'm on the project. I really think it's going to be a paradigm shift in how we as astronomers do our science. Python is a big part of that. We're learning to use it to do very efficient computation and to wrap computational tools in a way that non-programmers like astronomers can use easily. And I hope I've convinced you that reproducibility is a big component of this too. And I think Python being open source and being cross-platform is really going to be a help in driving that. So that's all I have, and here's my contact information if you want to get in touch. And I think we have a couple minutes for questions before lunch.
Questions?
It's a lot of data, and when you say that you're trying to sort of process that amount of data in real time, having to do all this computation, I can't stop thinking about it. It needs some sort of resource allocation prioritization mechanism. How does that work is one of the questions. And the other one is, what are your primary areas of focus? What you're trying to sort of see might be the unexpected. There's loads of stuff that you've shown, supernovas and all that sort of stuff. Okay. What is the main area of focus? Because if you see what I mean.
On the first piece, the resource allocation, that's kind of above my pay grade. You know, there is a huge team of people working on that aspect, and since my background is more astronomy than computer science, I haven't been as privy to those details. We have hundreds of people working on the project, and that's why I highlighted that Google is being contracted out for that. I can speak to the science goals, though. If you ask anyone on the LSS team about the primary science goal, you'll probably get a different answer for every person you ask. We like to think about this as a discovery class instrument. It's similar to the Hubble Space Telescope. When Hubble went up there, the primary science goal was to measure the expansion of the universe. But everyone knew that that would only be a small part of what Hubble actually did. And the data from Hubble have been used in every single area of astronomy. So I think the goal with LSST is actually to provide a legacy data set that can be used for pretty much everything. And there are definitely some trade-offs depending on what science you want to prioritize with the observing cadence and things like that. But we're trying our best to be as general and as broad as possible. So that's why I brought up all those different areas.
Thanks for the talk. And I have actually two questions. One is, which Python version and distribution are you using and why? And the other one is, what are we as a language and community and all the Python ecosystem not providing you guys?
That's good questions. Right now, we're using Python 2.5. Which you might laugh at. But the reason is because most scientists are working on systems that are maintained by a large IT department at their lab or university. And it takes a long time for those types of systems to be upgraded. So even to move to some of the more specific things in Python 2.6 or 2.7 would be a challenge, let alone 3.0. And so that's been a real challenge for us, and I don't see our particular project moving to Python 3.0 anytime soon because of the amount of legacy code there is and the challenge that it is to move between those two. So that's an interesting thing. I know some colleagues would be much more candid in answering your second question and saying that the thing we need you to do is as the Python core devs, the thing that we as scientists need you to do is not do things like release Python 3.0, because that just made everything crazy for us, which is why we're not adopting it. A big piece for us as well that we've been struggling with in the scientific community is packaging. And there are solutions like pip and virtual env that allow some things, but the problem is when you have packages like NumPy and SciPy and these other things that rely on Fortran and compiled C code, pip just doesn't work. You know, I've installed SciPy from scratch many, many times. I would never rely on pip to install SciPy. So we posed this question. I was at a PyData conference about 1.5 years ago, and we posed this question to the BDFM himself. And we asked him, you know, what should we do about packaging? How should can we help you as the core Python developers with packaging? And his answer was basically, we're not going to be able to do it for you. You should do it yourself. So Travis Oliphant and Peter Wang and some of the folks at Continuum.io picked up on that and have been working on this Anaconda project that some of you might be familiar with. And that's made a lot of good steps in the right direction. But still, the whole packaging thing is a challenge for scientists. Yeah.
More questions? Thank you very much for this amazing talk.
Yeah.
And see you in 1.5 hours.